Hello friends and welcome to this video. Here we are having the last topic from chapter 7, the chapter titled Wavelet Transform. This chapter we have studied right from addressing what are the origins of the wavelets and the wavelet theory. The complete development of wavelet theory we have been introduced to, and also the strong mathematical foundation behind the popularity of wavelet theory. That is why we are having the benefits of signal processing at the efficiency we have here. So now the comparison with respect to the Fourier family, which is also having a mathematical background, we have seen the lacunas of the Fourier family because of which the development of wavelet theory was made. We have seen, and right from addressing the practical wavelets from this family, which are so much popular as like the Dowage's wavelet, and the most wide research area that we have addressed in the previous topic, that it was multi-resolution analysis. Now it's time to see what are the applications of wavelet transform. Possibly I will demonstrate one of the application of the wavelet transform. So here we have the topic titled applications of wavelet transform in general. So let us begin with this topic. So here we can start with our topic, the topic titled applications of wavelet transform. So as we call wavelet transform, it is basically a mathematical tool. And what is the purpose of using the wavelet transform? That will be giving the details of applications of wavelet transform. So the peculiarity of wavelet transform, as we see, that is the use of wavelet transform for dividing a signal information into different scale components, is leading to variety of applications for the wavelet transform. So as we can have division of a signal information into variety of components which have different resolutions, I can say. So thereupon the resultant scale components having different scales, different resolutions can be studied with a resolution that matches to the object that is we are intending from the complete information. So this is leading to the variety of applications, and there are lots of applications possible because of this peculiar feature of the wavelet transform. So one of the application is data compression. The example is JPEG 2000. So JPEG, that is standing for the Joint Photographic Experts Group 2000. This is the version of JPEG. Whatever the images we generally store with the .jpg extension are of this particular file type. This is basically the image compression standard. So as far as we talk about the compression of any information is the representation of the original information with minimum number of bits. The benefit is that we can have saving into the storage memory for that particular information. Also, while that information is being transmitted from one place to another place, we can save the bandwidth also. So as far as image, to be a two-dimensional signal here, the image compression is possible. Basically simple JPEG, if you talk about, thereupon there it is the use of DCT, discrete cosine transform, the forward one and the inverse one, while we code that image or compress that image and decompress that image information, you can say. And here it is the another better version of the conventional JPEG, that it is JPEG 2000. Next to that, we can make the watermarking possible. So with the help of watermarking, we can have authenticity to the information that has been communicated over a communication channel. It can also be regarded as the subdomain of cryptography. So cryptography is basically hiding the original information so that there cannot be the losses made by unintended objects or the users into the communication channel. Also, we can have denoising, made possible with the help of wavelet transformation. So while practically working with signal processing, unintentionally or intentionally, there it is the addition of noise label to the original information, and at the receiver end we want the information to be noise free. So those particular signal processing methodologies we can categorize to as denoising here. So there are many such applications possible with the help of wavelet transformation. So as you can see, watermarking, I will make one demonstration into the MATLAB environment for image watermarking here. And also the characteristic feature of wavelet transform that has lead to all these particular applications is the decomposition of a signal at various scales or at various levels, I can say. So that also a small demonstration I will try to provide to you. So let us first of all switch to the MATLAB environment. So here we have MATLAB environment, and first of all I will demonstrating you the n level decomposition of image to be a two-dimensional signal, and that is made possible with the help of wavelet transformation, as we treat image to be a signal and the representation in the MATLAB domain as like the discrete representation. So here we have discrete wavelet transform that we can abbreviate to DWT here. So in this default view of latest MATLAB version, we will like to have untitled script. So initially from the editor window we'll take untitled script here. So I will mention the first line to be a comment line mentioning the purpose of this particular program. So here I write, this is a program for demonstrating n level decomposition of image signal using DWT, standing for discrete wavelet transform. So to get the fresh execution of our program, I will like to first of all close unnecessary MATLAB windows, clear unnecessary variables, those may be there in the workspace. Also the command prompt should be with clear screen here. Now we shall be performing n level decomposition here. So for performing the decomposition of image, there should be certain input signal available in the MATLAB environment. So from the current directory, we have to first of all read that information. So as you can see in the current folder on the right hand side, on the left hand side, we have 4 sample images as like cameraman.tif, lavender.jpg, lena.jpg, penguin.jpg. So these images we can read inside the MATLAB environment. So let us first of all modularize here the body of this particular script. So I will write input signal to be decomposed. So here what we shall do, we will define a variable capital A that will read the image information and be assigned to it. So the MATLAB syntax is imread within a pair of parentheses and a pair of single quotes inside. I shall be providing the name and the dot file extension of this image here. So I write here cameraman dot tif. At the end of this MATLAB syntax, I will provide a semicolon here. Now I will try to save this much of the program. So let us say I name it as program1. .m will be the file extension. Now you see this file has been created into the current folder, and the editor window label has also got changed with the name provided. So as we have saved this much of the script with the name, now we will try to run this much of the program and will check into the workspace whether the variable capital A is generated or not. So here I press run here. Now in the workspace you see there it is a variable capital A, and it is having the dimensions 256 by 256. the data type is of uint8 here. So after reading the image information and assigning it to the variable capital A, we shall be performing the decompositions of the signal information with the help of discrete wavelet transform. So I will have the first level decomposition. So writing first level decomposition to be performed here. So let us make the use of discrete wavelet transform, and here the syntax is DWT2 here, where the input arguments are to be provided and the output arguments are to be recorded here. So let us say we record the output arguments as M1 comma N1 comma we have O1 comma P1 here, and here we are making the use of DWT2 syntax. Inside we have the input argument as single capital A. Capital A is the input image to be decomposed here, comma in the pair of single quotes I provide dv1 here, at the end semicolon here. Next to that, what we shall do, we will define a variable capital B which is assigned the information first of all of uint8 type, that is from the variable m1, the output variable from the above step, comma it will be n1. By the next line in this array we will assign o1 information and then p1 information here. So this is the first level decomposition made possible. Now we shall go for the second level decomposition. Here we start second level decomposition. So for second level decomposition, we will have the output variables listed as M2, N2, then O2, and at last P2. Those can be obtained by again DWT2 in the bracket. Here we have M1 as the input argument, comma in the single quotes we have db1 here. So now you see, after first level decomposition, for the second level decomposition again we are making the use of DWT2. So DWT2 is working with discrete wavelet transform for two-dimensional signal. So now by the next line we shall define capital B1 to be the variable to hold the information of, we have M2 comma N2. By the next line we will have O2 comma P2 here, at the end semicolon. Next to that we will define B2 to hold the information of uint8 type for the variable capital B1 comma N1. By the next line it will be O1 comma P1 here. So this way we have the second level decomposition also made possible. So let us check whether we have the decomposition in alright way or not. So for that purpose we have to display the image information into the original form, into the first level decomposition form, into the second level decomposition form. So here I will write display of input and output images. So here for display purpose in comparative way I will make the use of subplot command. We will have one row, 3 columns, and assignment to the first cell. Here we make with the help of IamShow command. To this IamShow command we will have the input argument capital A, and thereupon we will provide a title to the specific cell of the subplot within a pair of parentheses and a pair of single quotes inside. We shall be writing original signal information. Next to that we will have the assignment to next cell of this subplot. So subplot 1 comma 3 comma 2 comma, we will be having again the use of IamShow command, and this time the input argument will be capital B, and outside we will provide the title to the specific cell as done before. So here we shall be writing label 1 decomposed image, and by the next we shall be having assignment to the last cell. So subplot 1 comma 3 comma 3 IamShow, the input argument is B2 here, and we provide the title as, here I write label 2 decomposed image here. So here we save this much of the script. In general we can go for n level decompositions here, but for visualization of the decomposition, whether it is happening or not, the 2 level decompositions are enough. So let us run this script. So as we run this script, there it is, a MATLAB pop-up window, a separate window here we have. As I maximize this window, you see in a single row there are 3 columns. So the first cell, here we have the title original signal information. The input image was cameraman.tif, here you see. Now in the middle we have label 1 decomposed image, that is the output of discrete wavelet transform or two-dimensional signal. Now you can see the original information, that it was into a certain dimension that we have checked, 256 by 256. It has been distributed into 4 parts. As you recall back the details of the wavelet transformation onto the two-dimensional images or two-dimensional signal here. So that time you will come to see that the trends into the image plane for the changes corresponding to the vertical direction, for the diagonal direction, for the horizontal direction are recorded, and they have been separated into the different parts. So for label 1 decomposed image, you see the image information has been separated into the 4 blocks. So there are 4 quadrants that you see. The first block is having the major information, that is better for display purpose. Rest of the components are having the age information that you can see. Now after label 1 decomposition, we have at last label 2 decomposed image displayed here. So what it is, first quadrant that you see, the cameraman with the instruments here, that has again decomposed into 4 parts here. So this way we can achieve n level decompositions by applying the wavelet transformation here. So this was the demonstration. Now as I have discussed earlier, few of the selected applications of wavelet transform, one of them is watermarking here. So let us have a demonstration of watermarking of the image with the help of another image that we call to be the key image here. So let us start with it. So for this purpose we will take a new editor window here. I will write the first line to be program or demonstrating image watermarking using discrete wavelet transform. So that is DWT here. So first of all, closing unnecessary MATLAB windows. Next to that, clearing the variables from the workspace, and then a clear command prompt here. So for watermarking purpose, we require image to be watermarked, the original image information. So as usual practice, here I will take capital A as a variable, and to this particular variable I will read the image information from the current directory or current folder here. So here it is the syntax, I am read. Inside a pair of parentheses, there should be the name of the file within a pair of single quotes here. So let us write it to be cameraman.tif. So here I modularize the body of the MATLAB script that we are generating here. So this is input image to be watermarked. So here we end this syntax with the help of semicolon. Now for whatever the cameraman.tif the image will be read here, we will get the two variables that will hold the dimensional information. How many number of rows, how many number of columns are there. So let us record them as the variables p and q here. So this information can be obtained if I make the use of MATLAB syntax to be size here. The input argument is capital A here, and onwards let us make capital A to be of double type for further watermarking here. So let us save this much of the script. So we will name this to be program2.m will be the file extension. So in addition to program1, here you have program2 generated to the current directory. And now as I run this particular program, in the workspace you see there it is a variable capital A, and that is with the dimensions 256 by 256, those two dimensional information, as we have the same number of rows and columns 256 has been assigned to P. And now we call this certain image for watermarking purpose to be key of watermarking here. So I just mention here generate the key for watermarking. So it will be the similar thing, but this time it will be the new variable capital B to read such key image. So let us say this time I take penguin.jpg as the image, the key image, and let us make this to be of double type. So as I save this much of the script and run it, you see in the workspace there it is another variable capital B in addition to the earlier three. So capital B is also having the same dimensions here. But if you are performing the watermarking with the images which are unequal in dimensions, so there it is a good practice to make the images of the same size. So with the help of IM resize, we can have the same size for the key image for watermarking with the original image to be watermarked here. So for the original image, the dimensions are marked to be P and Q. So with IM resize, we can provide these assignments here. Next to that, we start exact watermarking here. So let us modularize here. This is watermarking. So with the help of double percentage sign, you can have separation of the MATLAB script with the help of such a line, separation line here. Now here we shall require the weight for watermarking. So I just mention a comment, initialize the weight for watermarking. So let us define a new variable. Let us it be capital W, and the weight value initially I put it 0.001 here. Next to this, we require the use of discrete wavelet transform for performing the watermarking operation here. So for that purpose here I write compute the two-dimensional wavelet transform. So in this regard, let us have the output arguments to be the variables as CA, comma, let us see CH, next to that CP, and then CD here. So we are obtaining it with the help of DWT2 as the MATLAB syntax, where the input argument is A, and along with we have here DB1 for the dou, which is type of the wavelet used here. Now with the help of this particular wavelet, as we see the decomposition is done, and we get the signal information distributed into the four parts here. So what I have named here CA, in all these particular variables we have C common. CA stands for the approximate, H stands for the horizontal type of the information, V stands for vertical type of the information, and the diagonal changes into the image plane are recorded into the variable CD here. So this is what the application of forward discrete wavelet transformation to the original image to be watermarked here. Now we shall perform the watermarking. So for performing the watermarking, let us first of all define a variable capital Y, which will hold the information that we have obtained by DWT2 on the original image to be watermarked. So let us have CA and CH into the first row, whereas CV and CD to the next row. So let us have this to be the array. Let us define a new variable capital Z that we can obtain from this small y by adding it with the image B, which is multiplied by the weight as defined earlier. So image B is the key for watermarking, that also we have taken from the same current folder here. So after this, let us have the two dimensions, the new dimensions. P is equal to P divided by 2, then Q is equal to Q divided by 2, and let us perform the watermarking with the help of for looping here. Let us have the index variable I to initiate at 1 to extend up to the value P here, the new value of P. Next to that, inside we nest another for loop. So this time let us have the index variable to be equal to J. We initialize it again at 1 and to extend up to the iterations Q times here. Inside that, let us have the new components here. So we name it NCA, and the dimensions as we have the index variable I and J here. So NCA in the bracket I comma J, that is equal to capital Z of we have I comma J here. Ending with the help of semicolon, we go for calculation of NCV in the bracket I comma J here. At the end, we assign it with capital Z of I plus P comma J here. By the next line, we shall define NC H here of I comma J, that we can obtain by making the assignment of Z of I comma J plus Q here. At last, let us define NCD of I comma J. This we obtain by assignment of Z of, here we write I plus P here comma J plus Q. At the end, semicolon, and we get out of the for looping here. So here we are making the use of end keyword two times, as we have two for loops, one inside another. Now let us have the output image generated, that is watermarked here. So I just mentioned here output watermarked image. So let us define it to be capital C. See, the original image which is to be watermarked is capital A. The image which is acting as a key image for the original image is denoted by capital B, and capital C is the watermarked image, which will involve the contents from original image A and the contents from the key image B here. So here the image we obtain C by inverse discrete wavelet transform. So IDWT2 for the two-dimensional inputs here. Here we have the syntax and the input arguments. This time we will provide NCA, NCH, then NCV, then NCD. These we have developed in the for looping here, and here the type of the wavelet we are making the use DB1 here. DB standing for the dopages here. Next to that, we have obtained the watermark image. Now let us have the procedure to extract the key image from the watermark image. So I just mentioned here extraction of key from watermarked image. So let us make the use of discrete wavelet transform again. This time the output argument, let this be RCA, comma RCH, comma RCV, comma RCD here, and these we are obtaining by applying DWT2 for the watermark image that we have assigned to the variable capital C, and the type of the wavelet should be of the same one, that is DB1 here. So this is the computation of the two-dimensional discrete wavelet transformation here. Now let us define a new variable n1 that we assign the above information. So we have to the first row RCA, comma RCH. By the next row we will have RCV, comma RCD here at the end, semicolon. And let us obtain the extracted key from the watermark image, that is to be capital D, which we have obtained by subtracting Y from the N1 here. Now after this much of the procedure, there should be a display of the input and output images. So I just mentioned display of input and output images here. So here we are making the use of subplot command. So let us have 2 rows by 2 column, and the first cell is to be assigned. So for display purpose of the image information, we are making the use of IamShow command. So as we have the input image to be watermark A of the type double here, for display purpose we have to get it into the form uint8 here, and then we can provide title to it. So the title is original image. So inside parenthesis and a pair of single quotes, I write here original image here. By the next line, here we are making the use of again subplot, but this time the assignment to the next cell here. So 2 comma 2 comma 2 here, again the use of IamShow command, and this time it will be again the requirement into the uint8 type, but this will be the key image to be displayed here. So that is equal to capital B. Here we provide the title. So the title here it is key image for watermark. Next to that, we make the assignment to the next cell of the subplot. It will be 2 comma 2 comma 3. Again the use of IamShow command. So here it will be uint8 data type here, and you see the watermark image, that is the output image that we have obtained and denoted it with the help of capital C here. So here we provide title. So the title is output watermark image, and at the last we shall be displaying the image that has been extracted, the key image that has been extracted from the watermark image here. So here we will be having the assignment to the last cell. So 2 comma 2 comma 4, then the use of IamShow command, and here we are writing for the double type the variable d multiplied by 4 times here, and then the use of title to the specific cell displayed. So this is the key extracted. So as we run this particular script, you see there it is, a MATLAB window that has been popped up here with the subplots here. So 2 rows and 2 columns, so total 4 cells here we have. In the first cell we have the original image cameraman.tif that has been displayed here. In the next cell to the same row we have key image for watermarking, that it is penguin.jpg. In the next row, the first cell, that is the watermark image, which is from both the original image and the key image. And at last we have the key extracted from the watermark image, that we have obtained the penguin.jpg that we have obtained back here. So here it is, the maximized view of this particular MATLAB window. I just close it, and instead of using the penguin.jpg as the key image, if I try to change that one, let us say we have another lena.jpg, changing the name, saving the results, saving the changes, and running it again. So here you see the original image is the same, cameraman.tif, and now the cameraman.tif will be the image information holded up by the variable capital A. So capital A variable we have displayed here to the first cell of this subplot of 2 rows and 2 columns. Now in the first row, second column place, we have the key image for watermarking that we have used capital B as the variable. Here you see, instead of the penguin.jpg, now here we have lena.jpg. And now to the second row, first cell, we have the watermark image, the cameraman.tif, that it was the output image that we have assigned the variable to be capital C. And at last the second row, second element here, that is the key extracted from the watermark image, the variable D here, that we have obtained, that it is variable capital D, and for proper visualization we have multiplied it with the help of 4 as a constant here. So this way we have discussed the applications of wavelet transform. There are a lot of wavelet transform applications possible here. Selected are, or the popularity is for the signal compression, the image watermarking, for which the MATLAB demonstration we have seen. We can also demonstrate the signal denoising also. So this way we have completed our chapter 7, that it was wavelet transform. By the next lecture we will start with a new unit to our subject, advanced digital signal processing. The new chapter, it will be applications of signal processing. Thank you.